Okay, right, thank you very much. So I'm here to set the scene, and I've only got a few minutes, so I'm going to go very fast. But what I'm telling you, for most of you, is going to be very, very standard. The main lesson is it's old technology. This is not new stuff. This is old stuff. To give you an idea, hash functions. So what does a distributed ledger? It involves all sorts of bits of technology. So let's go through the history of how it's actually been created. So hash functions are not new. 1975, they were first come up with, in some sense. But we've had all sorts of hash functions over the years, and so these things are not new. The other thing that makes up distributed ledger technology is digital signatures. Digital signatures are not new. They go back to 1975. You can kind of think of them to a manual signature. But then you say, well, okay, but there's other stuff. You know, there's this Merkle tree thing. Well, Merkle is really ancient. Well, Merkle trees are really ancient. Okay? Sorry. So 1979, the idea of a Merkle tree came along to authenticate different data structure. And if you don't know what a Merkle tree is, why are you here? But anyway, so if you don't know what a Merkle tree is, if you want to authenticate the value x3, you just have to publish these values, and then you can go down, and then you know this thing. So it's a kind of very, very, hang on, you go, but hold on, distributed ledger is far more than that. It's about agreeing a ledger, and we all agree on the same thing. Oh my God, this is Byzantine generals problem from 1982, which is how do these Byzantine generals, or how do you agree, mutually distrusting people agree on a certain value? Which is exactly what you have in a database. If you have a distributed database, if you have an Oracle database, usually these are, you don't just have one database on one computer unless you're an academic, but if you're a big organization, you have your computer backed up in different places. You have to make sure all the records are consistent, the databases are consistent. This is a major issue in database technology. This is the Byzantine generals problem, okay? This is 1982, and you can deal with at most 1/3 traitors, theoretically. All this stuff about a half is rubbish. Yeah, it's 1/3, right? Okay, and we know, we've known how to do this, and there's loads of good protocols for this. But it's a cache. Electronic cache. This is a new idea. No, it's not a new idea. 85, David Chaum had this idea of digital cache to do financial transactions. And if you kind of think of this, the usual four-pronged thing, you have issuer, acquirer, customer, merchant. And so there was a company called DigiCash, I think it was in Holland, is that right? Yeah. That did survive for 8 years, which is quite good for an internet company in those days. Well, not really an internet company, well, sort of internet company. It is in the internet era, but kind of, yeah. But then you go, aha, and the actual idea of a blockchain actually came up in 1990 with a time-stamping thing where you had a set of documents, you wanted to collect them together, and you would create trees of these documents using a hash chain. So this is ancient technology. 1990, we have these things. In fact, there was even a company doing this called Surety Technologies in 1994. And it was also used in Estonia. Cybernetica, a company in Estonia, also did all this stuff. So up until 1994, we have all of the technology needed to do distributed ledger technologies. So why did it take until 2008 for someone to actually put it all together? Now, so Nakamoto's paper is actually really cool. He brings all these technologies together and combines them, and we get this lovely system, Bitcoin, which everyone's heard of, and I hope everyone in the audience actually understands. So what does it do? Is it basically uses a ledger. Now, a ledger is, in some sense, the thing that you have in finances, which is basically an append-only database. The word database is going to come up quite a lot in my talk, right? It's a database, and it's append-only because it's a ledger. You always add things to the bottom, yeah? So it's a ledger, and a ledger in banking or in finance allows you to record transactions, so that's what Bitcoin does. But you can record anything on a ledger, okay? And the thing is, it's a publicly verifiable ledger, which everyone can look at and verify that everything's been done correctly. Okay, that's the basic idea. So it's a ledger. So the whole key technology isn't the money, isn't the cryptocurrency, it's the ledger. And that's why this is called distributed ledger technology, is not a cryptocurrency day. Okay. So what is the ledger of reality? Okay, so as I've said, it's basically an append-only database. So a distributed ledger is basically a distributed database. That is not a modern piece of technology. Oracle has been doing this for years, right? So, and as with every distributed database, you need a way of having a consensus mechanism. And that's basically your issue with major installations of databases. So a blockchain is just one way of producing a database. But it's an interesting database because it only essentially allows append operations, which makes the ability to do the consensus easier than if you had like an Oracle installation, which allows you to do all sorts of weird operations. Okay, now in Bitcoin, you see the whole ledger. But there's a kind of difference. So in banking, you only keep the current state. You keep the balances. And so you actually know at the end of the ledger, you know, at the end of the day, what each account actually holds. So it's quite easy to work out, have you got this much money to spend? But in blockchain, you have to go back to the point where it's been actually assigned to the thing. So there's there are some issues, differences between how a bank uses a ledger and how blockchain uses a ledger. Okay, so there's a range of solutions you can have. So we have public blockchain, which is where you have a central point of control by wrong way around. No central point of control by individuals. It's permissionless to participate, and generally consensus is based on proof of work, or sometimes would be on proof of stake or other things. And examples here would be Bitcoin and Ethereum. You have a sort of consortium hybrid blockchain where you kind of control, there's a kind of halfway between the two. And a good example to look here was this RS coin proposal that came out of UC London and that was kind of motivated by putting things like RTGS on a blockchain in the financial services industry. If you don't know what RTGS is, I'll explain over coffee. It's quite cool, but it's very old. And then you have a fully private blockchain, which is maybe controlled by one organization. The permission is based on participation from the owner, so you really need to be told you can participate. But here, the readability of the blockchain could be public or could be restricted. So there's kind of different issues. One, whether you have public access to the blockchain in terms of read versus essentially the writing is done by completely permissioned. So, consensus. Let's look at the reality. So, many applications do not need a public ledger. Okay? We don't need everybody to read everything. We could have a provisioned blockchain, which is provisioned by the organization. So we don't really need proof of work, so we can actually do very, very, very fast consensus. Such a fast consensus mechanism that you can get huge throughputs on such systems. So there are many companies that have that give you provisioned blockchains, and the throughputs can be equivalent to every single payment in the UK. Yeah, so you could actually record everything. Well, I've seen some applications doing, okay? So in a public ledger, you have nodes which hold in ledger which you don't trust. These nodes are everywhere, and you don't actually trust them, so you need a way of solving consensus. And Bitcoin does this by mining. So let's look at some of the problems with mining. So what's the main problem with mining? Energy. So basically, we need the same energy consumption as Greece, okay? The whole of the Greece economy, the energy consumption is used for just the Bitcoin blockchain. This is completely unsustainable. So other ways of looking at this, you could look at the carbon footprint of Denmark. You could look at the electrical energy, it's comparable to the consumption of Austria. Electronic waste, that's just getting rid of all the computers at the end of their life cycle, is about the e-waste generation of a country the size of Luxembourg. Or alternatively, you could do apparently per year 723 visa transactions, or 48,000 hours of watching YouTube if you wanted to. You could do the power consumption of an average household over 20.5 days in the US. Or you can measure other stuff. So this is single transaction and analyze. So single transaction, we could do 720 visa transactions. This is not eco-friendly. Yeah, if you want green computing, this is not green. Okay, but the fact that it's expensive means that there's a market price. The market price seems to go up and up and up. So there's a kind of some people are making money just on the speculation here. Throughput. So I've already said that provisioned blockchains have huge throughputs. We can do massive amounts of throughputs. So non-provisioned blockchains are actually really, really, really slow. So the volume is low, time lag is appalling for modern finance, and if you're talking about crypto exchanges, one of the main problems crypto exchanges have is being able to switch money in and out of fiat currencies where they have to go back to their cold wallet, which is what they call their, oh God, I've forgotten the name now, transaction velocity is very, very bad for many crypto exchanges. So the number of transactions per day is not very many, you know. So we're talking like 400,000 peak for blockchain number of transactions, Bitcoin number of transactions per day. So that's a real problem. That's not very much, okay? If you imagine, that is like if you had like 4 companies the size of IBM trying to do their payroll on the same day. That's not very much at all, yeah? So it's way below the total number of transactions, even for a tiny country. Okay, so then we have the blockchain is public and we have transactions on it. So the transactions we can see. But, okay, so in Bitcoin we can see how much is being transferred, but we kind of hide-ish who the transactions are corresponding to, but we don't quite hide. So how do we actually get real anonymity? Bitcoin doesn't give us real anonymity. So how can we have a public blockchain that people can look at, but they can't actually see the data on it, but they can still verify it's correct? So there's this system called Zero Cash, which basically encrypts in some way all of the identities and the values. And then what you have to do is prove, in what's called zero knowledge, that these transactions are valid. And everyone goes, oh, but this is a super duper duper modern thing. And actually it's not. It goes back to 1989 by Goldwasser, McCallie and Rakoff. It's an ancient technology of zero knowledge proofs. But the blockchain ecosystem has actually created some new zero knowledge proofs that you might have heard of. So this slide is probably the most interesting slide in the talk, actually. For those of you who want to take photos of any slides or take any notes, this is the most interesting slide. So in the blockchain world, you see a bunch of different types of zero-knowledge proofs. You see things called snarks, starks, and bullet proofs. And they all have different properties. Now imagine, so a proof, all the phones are coming out now, yeah? So the issue is, on a blockchain, you've got to put the proof on the blockchain. So you really want a small proof. Good. Okay, so we want the size to be small. Also, bullet proofs are small, so that's quite good. Sorry. 3's good. Yeah, they're 3. Snarks are small. But we want bullet proofs are kind of small, but starks are not very small. Then you want to be able to generate the proof quickly. So if you're actually putting a transaction on the chain, you want that to be fast. But you also want someone to be able to verify the transaction on the chain to be fast. And you also might be interested in whether it's post-quantum secure. And you can see from this table, no technology gives you everything. So actually, these zero-knowledge proofs do not really solve every problem we've got on a commercial tech. So all of this negativity, it must be cool for something. Well, Gartner thinks it's cool for something because it's everywhere. Cryptocurrencies, Gartner. You know, this is weird. Well, okay, it's on the slide down, but we're kind of up at the point where people should invest. Yeah, so it's a really, really popular with Gartner. It's popular. That was cryptocurrencies. This is blockchains. Is really, really popular on the Gartner hype cycle. It's popular on other Gartner hype cycles and more Gartner hype cycles. You know, so this is really, really, really big, and there's more Gartner hype cycles. Yeah, so this is very, very big. So the question is, do we need a blockchain? This is my last slide. Okay. Do we need to store a state? No, so we could put it in a database. Do we need multiple writers? Yes. If we don't need multiple writers, use a database. Do we need a trusted party? If the answer is yes, you probably want to use a database. Are all the writers known to you? Yes. Well, then you've got to ask, are all the writers trusted? If yes, use a database. If no, use a permissionless blockchain Do you need public vulnerability? Duh. So basically, in almost every single one of your applications, use a database. That's it. Thank you. Use a database. So at every talk today, what you've got to think of is there are applications where you can use blockchain. I'm just trying to be controversial, right? So there are applications where you can use blockchain. But in every application you see today, you've got to have at the back of your mind, can I use a traditional database? Yeah, and if the answer is yes, then the question is, is it more efficient to use a traditional database, or am I only using blockchain so I can get investment off a stupid VC fund? Which is often, and if that's the only reason you're using blockchain and you need the money off the VCs, then use blockchain. Thank you.
Thank you very much, Nigel. So we have time for a couple of questions, if there are any.
Surely I can store the state and have multiple writers in a database.
Yeah.
You've got no there. Why? What? You know.
So can I store the state and have multiple writers in?
On a database. Yeah.
Oh yeah, but the point is if you don't need multiple writers, go straight for the database. Yeah, there's no need to use a blockchain. Yeah, you might as well go straight for the block. Yeah.
We have a question there.
Oh, yeah, you were first.
How do you know if you can trust the writers?
Oh, but that could be a business case, yeah. I mean, that's dependent on. So, for example, if you took the RS coin example when you were doing RTGS, the Bank of England would be for example, your central bank would be the main authorizer, and then they would trust the writers because the writers would be the tier 1 banks, otherwise the clearing banks. So, with that application, you kind of know it. It's kind of inherent in the system.
Do they though?
The Bank of England does. If you trust,
they really trust. Do banks really trust each other?
the Bank of England trusts them. So if you then do a if you read the RS coin paper, you kind of get the thing. Yeah. Oh no, hold on. Who's first? Go the back, right at the back.
But just, I think databases are too many connotations of structured data and SQL and stuff. You can just use GitHub. It's fine.
Good point. I should use GitHub as well. Yeah, that's a good one.
Shall we ask our next speaker up front while you take?
Yeah, that's a good idea. Yeah.
That's okay.
Right, keep going.
So the Zcash fellows tell us that they are using zero-knowledge proofs for all of their anonymity needs.
Yeah.
And this strikes me as odd, because if we go back to the Goldwasser-Macaulay paper, zero-knowledge proofs were principally used to prove things that the other party could observe, or prove things that the other party knows. It's just a matter of saying that I'm demonstrating to you that I know some secret that you also know.
No. It's in a zero-knowledge proof, and if you go back to Macaulay, it's I'm demonstrating to you I know something that you don't know, but it satisfies some relation. So, for example, I'm demonstrating to you that I've got enough money in my account, but I don't reveal how much money I've got in my account. I just tell you that I have enough money to spend this amount. So, start again. Very quick. Right. Okay. Because this is important. Right. Okay. I have two values: X, the amount of money I'm going to spend; Y, the amount of money in my account. I need to prove to you that Y is bigger than X. That's it. I don't tell you what X is, I don't tell you what Y is, just the zero-knowledge proof tells you that Y is bigger than X, that I have enough money in my account. That's what the zero-knowledge proof can give you. It doesn't quite do that in zero cash, but, well, it does a bit, but yeah.
Don't you require a trusted third party for that?
No. Depends. Well, no, depends. That's the whole point, is that you need a trusted third party if you use this CRS model, blah, 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 depends on the type of zero-knowledge proof, So, subject to technology, you don't need a trusted party to actually do that. That's the whole magic of zero-knowledge proofs.
Do you have any papers on that?
There's gazillions.
See, I'm creeping up here.
Yeah, I know, yeah. Whoops,
But
where's my
we
thing?
need to just hand over the microphone.
Yeah, that's what I'm doing.
We'll introduce next door. I can see Nigel is